Okay, so if you recall from last week, we said that to use linear programming, there's a lot of things we can use linear programming to solve, right? We already saw just a few examples, production mixes, obviously, portfolio models, we saw diet mixes, blending models, cash flow models, ones we'll talk about in the future as well. But we said last week that we have to make a lot of assumptions. You know, we have to assume the parameter values are known with certainty. And honestly, we don't know. We assume we're going to make 150 bucks for this unit, but we don't know what the market's going to do. We have to assume constant returns to scale, that if it costs me $5 to make unit 1, it's going to cost me $5 to make unit 2, and the millionth unit is also going to cost me $5. And that's often violated. We assume there are no interactions, and we assume continuity assumptions. Sometimes we violate that. So we may begin to question, like, why is this useful at all? Okay, if we have to, all those assumptions, we know those don't match what we do in practice, then why even do this? Well, a couple things, okay? It's better than no information is one, but the other thing is, a lot of times we're going to get an answer that is what we call a robust solution, meaning it's valid for a bunch of different variables, not just the ones that we've assumed. We've assumed 100 bucks and 150 bucks, but this may be good even if the profit goes up to 120 or it goes down to 80. So what we want to do today is we want to do something called sensitivity analysis of the optimal solution. So once we have a solution, okay, once we've set it up, we've put it in Excel, we've solved it with Solver, now as managers, we want to start asking deeper questions. What's holding me back? We've done that a little bit. What if this variable changes? How much is this worth to me if I get an extra unit of this? That's what sensitivity analysis is all about, okay? So it answers these questions. Is the optimal solution sensitive to changes in input parameters? Question one. Possible reasons for asking this question? We mentioned this before. The parameter values we use were only best estimates. They're not exact figures. The dynamic environment may cause changes. The economy may shift, whatever reason it might be. And what if analysis may provide other operational information? What if we change this a little bit, then this now comes into play, becomes more optimal. Okay? So the first thing we're going to look at, and bear with me here, I'm going to go through the slides, and it may be a little bit theoretical, it may be a little bit non-concrete at the beginning, but then we're going to try to apply it to one of the models that we've used. Okay? We're going to try to apply it to something that we've done, and I want to show you what that is. So the first thing we're going to talk about is the range of optimality. Okay, ROO it's abbreviated as, the range of optimality. The range of optimality says for an objective function coefficient, okay, the optimal solution will not change as long as the objective function coefficient lies within this range. Okay, lies within this range of optimality. If we go back to the space ray and zapper problem, let's pull up the space ray and zapper problem, and I'll pull it up. Let's see if we can find it here. Space ray example. Oops, that's not the one I wanted. Space ray and zapper. All right, so you guys recall the space ray and zapper was something, it was a production mix. We made $8 for every dozen space rays, $5 for every dozen zappers. We had things like plastic, time, and we had 2 marketing constraints involved. So I solved that, and you guys have done this before, but I solve this. I click solve, and I get a solver solution, make 525 zappers, make 175 or 525 space rays, 175 zappers, and I make profit of 5,075. Okay, and this might not match exactly what we did. I might have changed some things, but it doesn't matter for this solution. After I do this, I want to click on show me the sensitivity report. You guys see this over here? It says reports. Click on sensitivity. And then click OK. And if you notice, it's going to give us an additional worksheet that says sensitivity report. Now I'm going to show you how to interpret that sensitivity report. The first thing we're going to look at is the range of optimality. Okay? The objective function coefficients was 8 and 5. We made $8 for every space raise and $5 for every zappers. Well, my question is, well, what if we don't make $5 for every dozen zappers? What if we don't make $8 for every dozen space rays? What if the market conditions change? What if our cost accountant gave me a bad estimate? Whatever it might be. Well, there lives in here something called the range of optimality, and you have to calculate it from the sensitivity report. According to this, our current profit coefficient for space rays is $8. If you see, it says the allowable decrease is $3. So that means if we decrease the $8 by $3, we get to 5. And the allowable increase, and this is an awful way the way Excel expresses this, but 1 times 10 to the 30th, which is basically what? 1 in 30 zeros, which is, for all intents and purposes, infinity. So the range of optimality for space rays in this case is from 5 to infinity. Just bear with me. For zappers, the current coefficient is $5. The allowable increase is 3, so that's 8. And the allowable decrease is 13. That's not good. Okay. Now let me just explain. I don't know why that says allowable decrease is 13. The allowable decrease is 13, so that means -8 is the range of optimality. Okay, so 5 minus 13 is -8. Now what this is telling me, okay, even if zappers goes up to $7, even if we start making $7 per dozen zappers, guess what the solution is? It is still the same solution. It is still make 525 space rays and 175 zappers. As long as it's in that range, this is still the optimal solution. Now what would happen though if I start making $7 for every dozen zappers? 525 and 175 is not going to change, but what does change? The profit change. Let's see. If I go up to and change this to 7, and I just resolve, nothing changed. Okay? Well, the profit changed, but my solution didn't change. You guys notice that? If I go down, well, let's go take it back to where it was, 5. And if we look at the range of optimality for space rays, it's from 5 to infinity. So if I go down to, let's say, $6, and I resolve, is anything going to change from the 525 to 175? It's not, because it's in the range of optimality. Now if I go beyond the range of optimality, let's say I go down to $4 for space rays, outside of that range. Let's go to 4 here and resolve. It's no longer within the range of optimality, so it does change. I know why. I don't have that set. Okay. As soon as it went to outside that range, it changed the solution. Do you guys see that? Okay. So what the range of optimality says is as long as those coefficients are in that range, we have nothing to worry about. I know why I didn't have the non-negativity on. Now I do, so it looks a little bit better. Okay. All right. What was it, 8 and 5 to start with, right? Let me resolve it. Get it back to where it was. Okay. And here's what's happened. This is why I showed this to you last week. You think about it, what was this called, this area, this green area? What do we call that green area? It's called the feasible region. These are all the values that are possible as defined by the constraints, yes? And if we send this profit line out, this is the optimal solution, the last point it touches. If we change the 8 or we change the 5, what are we in essence doing? We're changing the slope of that line. But guess what? Even if we change it to 4x1 plus 5x2, it doesn't change the slope enough that that's not still the last point it touches. Until it goes beyond there, okay, until it goes beyond there, then another point becomes optimal. So the range of optimality gives me the range of values, okay, the range of values within, okay, that coefficient, if it remains within there, that my final solution does not change. And when I talk about final solution, I mean my decision variables.
So what if you change
both?
Yeah, what if you change both? Is this still covered under this?
No. That's a very good question. If you look, okay, if you look at the definition of range of optimality, it says optimal solution will remain unchanged as long as an objective function coefficient lies within its range of optimality. So that's what we calculated. And there are no other changes in any other input parameters. So if we change both, it's kind of off, right? If we change one, though, kind of look at it and we can see, hey, this is going to be all right. We're still going to have the final solution. Now, what this tells us, if you think about it, if I have a big range of optimality, like, I don't know, like the corn and barley, I can't remember, but I think it was like 50 and 100, okay? And maybe the range of optimality was 25 to 100 for the corn, and maybe 50 to 200 for the barley. Well, what does that give me in my solution? It gives me more confidence that, hey, not only is this the right mix to make if it's 50 and 100, but even if it's somewhere in this range, if it goes down 50% or up 150%, I'm still okay. You know what I'm saying? I'm still making the right amount of corn and barley. If it's a real tight mixture, maybe it's like 49 to 51 is the range of optimality. You know what I mean? There's not much wiggle room. What is that telling you about the final solution? If there's not much wiggle room for that optimal solution, what does that tell you? What's that? Your assumption better be right. That's a good way to say it. The other thing it tells you is a small change will make another solution optimal. You know what I'm saying? Like if you picture it on your graph, when we say it's a very small, that means it's like right here, and a little change, one of those objective coefficients, makes a whole other point optimal. You know what I'm saying? So maybe you want to investigate and see what that other point is, and see if it suits you better managerially. Okay? It talks about the robustness of the final solution. That's called the range of optimality. Let's look at some of the other things in sensitivity now. So I'm going to skip reduced cost, and I'm going to come back to looking at our constraints. Let's look at our constraints. One thing that we might want to look at, and I asked you guys this, I said, what is holding us back? What is binding? Binding constraints are things that are satisfied with equality. We've used all of it, right? We've used all of it. So we can also look at that right-hand side constraint, and it can give us some information about what would happen if we get an additional unit of this factor. In sensitivity analysis of the right-hand side of constraints, we were interested in the following questions. Keeping all other factors the same, how much would the optimal value of the objective function change if the right-hand side of the constraint changed by 1 unit. As well, for how many additional or fewer units will this be valid per unit? All right, let's go back to our space ray and zapper. I'm going to show you this. So I'm going to resolve it just so I have a fresh solution. And I'm going to keep the sensitivity report. I'm sorry, that one wasn't set up right. Let me find the one I have that's set up right. I don't know what that one I pulled like, but that wasn't a good one. Let's look at this one, okay? I think this was the solution we got when we did in class, right? 320, 360, okay. So let's go to this one, and let's go to the sensitivity analysis and take a look at this. Let's look at the solution first, and you guys tell me, what is holding me back here? Let's look at the constraints. What is holding me back? What am I using all of? And? Okay. Those are what's called binding constraints. They're the things that are holding me back. If I go to the sensitivity report, we can see this in the bottom as well. Plastic total, final value was 1,000, we had 1,000. Production time was 2,400 minutes, and we had 2,400 minutes. Now what you'll see for those as well is something called the shadow price. The shadow price for plastic is 3.4. The shadow price for production time is 0.4. Let me explain what this means. If we get an additional unit of plastic, one additional unit of plastic, our profit's going to increase by what? $3.40. If we get 2 additional units of plastic, our profit's going to increase by $6.80. If we get 3, it's going to increase by what? $10.20. For every additional unit of plastic we acquire, our objective function coefficient will go up $3.40. Does that make sense? So it's telling us, hey, this is what's holding you back, and an additional unit of this resource would help you make an additional blah. That's what the shadow price represents. Let's try it out. Let's go back to my Galaxy Industries, and let's say my plastic went up to 1,001 units. According to this, my profit, if I resolve, should go up to what? $4,363, and let's see if it's right. I'm going to click Solver, Solve. Taking some time, but it comes back and it goes up to $4,363.40. That extra unit of plastic, now we know what it's worth. This is what's holding me back, and this is how it's holding me back. This is how much an extra unit of plastic is worth to me. Now, can we just keep adding plastic and adding money? Can we add million unit of plastics and just keep pumping up the money, keep pumping up the profit? What's going to happen eventually? Something else is going to become binding, right? Something else is going to hold me back. Yeah, now plastic isn't an issue, but maybe, maybe total production is, or maybe this marketing constraint is. So we need something else to help us, okay? And that thing that we need to help us is called, oops, so let me take it back to where it was, 1,000 here. It's called the range of feasibility. So the range of feasibility you have to calculate just like you have to calculate the range of optimality. For plastic, let's focus on plastic. The final value is 1,000. Our shadow price was $3.40, which is under shadow price. The allowable increase is 100. So 1,000 plus 100 is 1,100. The allowable decrease is 400. So 100 minus 400, 1,000 minus 400 is 600. This is known as the range of feasibility. What it is telling us is this shadow price is valid anywhere in that range. If I get an extra unit from 1,000 up, I get an extra $3.40 profit per unit. If I lose a unit of plastic, it gets melted or whatever happens, I lose $3.40. If it goes beyond 1,100 or beyond 600, all bets are off because something else has become binding. You guys see what I'm saying? For example, let's try it. Let's say I get an extra, so the range of feasibility goes up to 1,100. So let's say I go up to 1099. Oh, wrong one. Let's say I go up to 1099 here. And I resolve. My profit is going to go up by 99 times $3.40, and it does. Okay? If I go beyond that range of feasibility, let's say I go to 1150, I click solve, I click solve again. Okay? Something else became binding, and I didn't get that same result. You see now what became binding is the total production is now binding. So if you picture it, we try to picture this in the sensitivity that we showed. What's really happening, and this is the galaxy in space for A1, the two things that are originally holding us back were production time and plastic. If we get extra units of plastic, it pushes that line out further, and what happens is now more points become feasible, which means I can push my profit line out a little bit further. But there reaches a point, okay, which is $3.40, but there reaches a point where it's only effective until a new constraint becomes active. I can keep pushing it out, and at some point, something else is going to be holding me back. The range of feasibility tells me where is this shadow price valid at, if you will. Does that make sense? So they work in concert with one another. Help me, because we just did that one together. I'm going to go back to the original solution, so let's put 1,000 here again. Let me resolve it. Yeah, let me put 1,000 there again. Let me resolve it. Keep the new sensitivity report. I want you guys to help me analyze production time. Is production time binding or non-binding in this solution? It is binding or non-binding? That's the first question. Is something holding me back? It is. How much would I lose? How much profit would I lose if I lost 1 hour of production time? How much would my profit go down? 40 cents. If I got an extra unit, it would go up 40 cents. Where is that range valid at? Let's see. Currently it's 2,400. The allowable increase is 100, so 2,500. The allowable decrease is 650. So that is what, 1,750. So anywhere between 1,750 and 2,400, I would get 40 cents up or 40 cents down for extra unit of production time. Does that make sense? Those two things work together. Now, one other concept with this, and this is like a little bit tricky. If someone says, we normally pay, let's say we normally pay $1 for a pound of plastic. Okay? We normally pay $1 for a pound of plastic. If someone asked me on this final solution, if I want to buy 50 pounds of plastic at $4, would I say yes? $4 a pound. Would I say yes? You're probably saying no, yes? Why are you saying no? Tell me why you're saying no. Read.
We're only gaining $3.40.
Okay. Why pay $4 when the profit's only going to go up $3.40 per unit, right? Doesn't make sense. Well, the thing is about plastic, most likely it's an included cost. And what I mean by included cost is someone came up with this coefficient, right? Someone came up and said, we make $8 for every dozen of Space Rays and $5 for every dozen Zappers. How did they figure that out? How did the cost accountant figure that out? They started with what we think we're going to sell for it, and what did they subtract out of there? Expenses including what? Labor, including the material. So already baked into this $8 and $5 is the $1 we already pay for the plastic, that we originally paid for the plastic. It's already baked into these coefficients. Does that make sense? It's already factored in. So the way we interpret this shadow price is not the amount we're willing to pay, it's the premium above the normal price we're willing to pay. We're willing to normally pay $1, so we'll be willing to pay not just up to $3.40, but up to what? $4.40. So the correct answer to this is yes, I do buy it, okay? Because I make a $3.40 extra, but that $1, okay, is already baked into that profit coefficient. Does that make sense? It's an included cost. It's already factored in. So the way we interpret shadow price is the premium above what we normally pay for that product, or normally pay for that production item, okay? Because it's an included cost. I know that's a little deep, but that's what it is. So the correct answer to that would be yes, we would be willing. We'd be willing to pay up to $4.40 for every extra pound of plastic within that range of feasibility. All right? Let's look at one that isn't binding. Total production isn't binding. It does have a shadow price, but the shadow price is 0. It has a range of feasibility. Right now, it's saying 700 is the limit. The allowable decrease is 20, so that's 680. The allowable increase is infinity. So what this is saying, think about what it's saying. It says, our profit won't change if that 700 goes up to infinity, doesn't matter, doesn't change our profit, or if it goes down to 680. But once it goes beyond 680, it's going to be impacted, right? Because right now we're making 680. We make less, we make that more binding, it's going to start factoring and start going to hurt us. So that is shadow price and range of feasibility. We're going to do one of these together to make sure you understand it, but let's just go through the slides here. The last thing, and this one, the last bit of sensitivity is a mouthful. It is called something called reduced cost. Okay? And reduced cost works like this. Assuming there are no other changes to the input parameters, the reduced cost for a variable that has a value of 0 the optimal solution is. Okay, and there's two things we can look at it as. It's the negative of the coefficient increase of the variable necessary for the variable to be positive in the final solution, or is the change in the objective value per unit increase of x. All right, now I know that was out of left field, very theoretical, but let's take a look at it. If I change this slightly, let's make it so that zappers are ultra profitable. Let's say we make 25 bucks for every dozen zappers. And let's resolve this. Let's click solve. And as expected, it moved all production to zappers, right? Because it's the more profitable product. It moved all production to that. I kept the new sensitivity report, if you noticed. And it's going to have a reduced cost for space race. And the reduced cost is negative 10.75. It's telling us two things, and I'll go back to the definition in a second, but in human terms, it's telling us two things. It's the negative of the increase necessary for this to become positive in the final solution. I'm not making any space race. It's telling us that I have to increase this coefficient by the negative of that, which the negative of a negative is a positive. For me to start making space raise, their profit would have to go up to at least $18.75. You know what I'm saying? For it to become profitable for us to shift some production from zappers to space rays, this number would have to increase to $18.75. That's one thing it tells me. The other thing it tells me, it says, if I say the hell with it, I'm going to make a dozen space rays, which I'm entitled to do, my profit's going to go down by $10.75. Let's look at that definition again after that explanation. It said this, okay? It said this. It is the negative, remember it was negative 1075? It is the negative of the objective coefficient increase of the variable necessary for the variable to be positive in the final solution. We'd have to increase the negative of 1075 is positive 1075. We'd have to increase that 8 up to 1875 before we're going to start making it. That's the first thing it says. Let's test that out. Let's see if that's the case. If I go to this, go back to if I make this $16, hey, that sounds pretty profitable. If I resolve, is it going to make any space raise? Is it going to make any space raise? No. It's still not profitable enough. If I go to $18, is it going to make any space raise? Let's try. Resolve, no. Still no space raise. If I go up to $19, is it going to make space raise now? It is. I don't know how many it's going to make, but remember 1875 was that threshold. We're over that threshold now. I click solve or solve. Hey, we're back to our original 320 and 360. Okay, let's go back to where this was. Was it 8? I think it was 8, yes? Okay, I'm going to resolve. And we make 15,000 according to the solution. I'm going to add a constraint to force it to make a dozen space rays. So I'm going to say add that B4 has to be greater than or equal to 1. I'm forcing it via a constraint to make a dozen space rays. And it will, because it's a constraint. It'll do whatever the constraints tell it. What's going to happen to my profit? It's going to change by what? It will. It'll change by 10.75, and it'll go down by $10.75. Okay? And it did. So once again, what the reduced cost tells you is two things. You'll only have a reduced cost if the final value is 0. You'll only have a reduced cost if something is 0. If something's not part of the optimal solution. You notice we're making zappers, and it has a reduced cost of 0 because it doesn't factor into play. It tells us two things. It's the negative of the increase necessary for this to be positive, as well as the change that will happen if I force 1 unit of production of that item. So how can we use this? Well, say we have a whole line of materials. Maybe we're making 10 different items. It's a production kind of thing. And one item says it's not profitable to make this in the final solution. As a manager, you can look at that and say, well, maybe we're not charging enough for it. What would it take for it to make sense for us to make this. Maybe we have to charge more for it. The reduced cost could tell you how much more to charge for it. Or if you want to say the hell with it, we still want a nice production mix. We still want a nice marketing mix. We still want to offer products all along our line. We want to make them. We have to realize, hey, that's going to take resources from more profitable items, more profitable things, and this is how much it's going to cost us exactly. So all these things with sensitivity analysis are what's called post-solution analysis, okay? Post-hoc analysis. We have a solution, but we're not quite satisfied with it, or we want to understand the solution more, or we want to ask what if. Now all these things have certain requirements. You know, he mentioned, what if I change two things? Well, bets are off. Okay. What if it goes beyond the range of feasibility? Well, you pretty much have to resolve. But because we have it in something like Excel, it's very easy to change the values and do some what if analysis. All right, I want you guys all have your laptops. Let's start the homework. I want you guys to try one. Maybe. I would like you guys we did 2A for homework for this class. Do B and C. Okay, B and C. So we did 2A on page 101. Do part B and C as well. So this is asking us to interpret things in the sensitivity report, B and C.